Lecture today is on grid-based fastslam. Last time we've seen fastslam when we have landmark-based map. Then we've seen how to bit of refreshing on how to compute grid maps. So if you go with the occupancy grid framework or on the using the Bernoulli likelihood and the maximum likelihood maps and so on. And today we'll see how you can use the knowledge on fastslam, the knowledge on grid maps, and put them together and doing what we call grid-based fastslam. Go back on the bit of motivation around here is that we just have seen landmarks so far, and we've seen that landmarks are good if you want to localize yourself, or a good way of compactly representing environments by just using a few points. But they might have a disadvantage in case you want to use these maps also for planning, or if you want to know which part of the environment you can safely traverse, which part you can't, and since you just have a few samples of the obstacles, you are never sure if whenever there is no landmark, if actually it's free to navigate or not. No? So since we know how to build grid maps, let's try to see how we can integrate these two problems, like localization and mapping, when we have this kind of representation. This is what happens if you just try to say, okay, I have odometry from the robot. Let's just take the raw odometry from the robot, use this as a known pose, and let's use the occupancy grid framework, or anyway, do mapping with known poses using the odometry as the known pose. And the problem is that you get a lot of noise in the odometry, and when you try to put all the laser data on top on this map, you get something which is not really usable, okay? And the problem here is that, especially here, the robot was rotating a lot, and there is a lot of noise accumulating during rotation, and there was a mess in this area. Here you can see that the robot is actually trying to go straight, but there is a bias in the odometry. It can be that one wheel is maybe has less air, or it's a bit unmounted or wrongly calibrated, and you see that it's basically kind of doing bended corridors and so on. So these are typical errors you find in odometry. You can calibrate this, you get slightly better, you can have very good odometry, you get again better results, but eventually there will be small error that is always present. It's almost impossible to remove it. There can also be that there are some stones on the ground, so you have perfectly calibrated odometry, but it just jumps on the stones and then it slips and so on. So you will eventually get lost. And the idea when you do SLAM is that you try to correct this drift, you try to correct this error by analyzing the environment around you, so by using the laser data or the sonar or whichever sensor you have, or a camera or so. So just to say is, can we actually now solve the SLAM problem if we don't have landmarks, if you just want to use the raw data that are given from our sensors, and also can we use the same idea that we used in fastslam to actually apply to the raw data. If you remember fastslam, what basically we had is we look at the full SLAM problem, so we estimate the full trajectory of the robot and the map, and before we said this was a set of landmarks, and now this is a full occupancy grid map. And again, we have our sensor and our control, or you can say the exteroceptive measurements, the one from the outside, and the proprioceptive measurements, the one that comes from inside the robot, like the wheel encoder or so on. This again can be factorized in these two products. We have a path posterior that we again will use a particle filter to estimate. And we have a map posterior where we, given the path, we can use mapping with known poses for doing that. Okay, so in the previous fastslam approach, we said this was a set of landmarks, so we could use a set of independent Kalman filters for solving this. And right now we are saying this is a grid map, so it's an occupancy grid, and we had in the previous lecture a way of computing analytically the statistics of these grid maps given the pose and the measurements. Now, again, as in the case of the landmarks, this map depends on all the poses that has been, so all the trajectory of the robot over time, and of course on the data that has been collected along this trajectory. We can say that mapping is easy if you know the poses with what would be seen with mapping with non-poses. And if you look again at the structure of the grid-based LAM, we have the same structure as we had with the landmark. The only thing that changes is the nature of this variable here, which is the map, and also the influence or the conditional distributions of the map, of the observation given the map, okay? Because we are not having this landmark measurement model any longer, but now we have this observation model we've seen for instance, the same that we've seen for the localization problem, where we know we can do ray tracing on the map, and we can say, okay, this is where my observation should be, and then I'll take the same beam, and I say, okay, that's the difference between the observation, this is my likelihood, okay? The difference between what I expect, taken from the ray tracing, with what I obtain, we put the Gaussian up there, and so on. So that's what we change, this representation and the measurement model. To be able to represent the full SLAM problem with, again, the same factorization, again, call it Rao-Black equalized particle filter, where we have just one part sampled, the path posterior, and the other part analytically computed. We have to give to each particle a trajectory of the robot, so as we did before for the landmark, but this time we also need to maintain a known map. And this can create also memory problem, because before we had a set of n landmarks, and now we have to give a complete environmental representation. So for the same area, the amount of data that we have to collect is actually more than what was before, okay? Now, here is an example of how this can look like. We have right now 3 particles, and each of them represent the trajectory. Here is just the last pose of the trajectory. And you can see the map associated with the different particles. And for instance, in this case, this is the trajectory of the robot. This is the map built by using occupancy grid with known poses. So the trajectory is known in this case. That's not good. Okay, now let's go again. Here in this case, we have a different hypothesis, so the trajectory is slightly different, the map again is slightly different, and so on. Some of them might be better, like this one looks quite good, this one looks okay, this one looks quite bad because there is some mismatch up here. And the whole goal of the filter is then to find out which are the best particles and then eliminate the bad one during the sample, and so on. If we just apply exactly what has been done by fastslam 1, so we just use the odometry as proposal, and we then use the likelihood for computing the weights. And we try to do this in a way that it's computationally feasible, so that we don't run out of memory. So we have to limit the number of particles so that we can still keep them in memory. That's what we obtain. So the problem here is that memory requirements are much higher, and therefore we need to find a way of reducing the number of particles, and still have a quite good representation of the distribution, of the posterior distribution, to be able to effectively get a map which is actually of a good quality. So how can we do that? The first thing is that we need to improve the pose estimate, since that's the only thing that is done, is used a particle filter, so it's sampled from. We should find a better estimate of the pose, either before applying the particle filter, which will be the first solution, or to find a better way or a better proposal for the particle filter in this case. The first idea here is that we can use a scan matcher. So a scan matcher is a technique that takes 2 scans and tries to align them together in a way that the overlap between the 2 scan data is maximized. Okay? So in some sense, you can imagine that I'm trying to have a single map, which is a very simple map, and it's made by a single scan that I acquired my previous pose. And now I'm trying to localize myself with just 1 scan on the previous map. Okay? And you can do it with the different ways. There is several techniques for doing this. We're going to explore them later on in the lecture, but here what we try to do is that we try to find the maximum value of the robot pose at times t, such that it maximizes the likelihood given the map that we have so far, and you can imagine it can be composed out of one scan, the pose that we are trying to find, the observation we have right now, and also considering the fact that the robot moved from the previous pose, okay? So we get the maximum a posteriori estimate for this pose, xt star, and we use this as our improved odometry measurement, okay? So if you now want to give a comparison on this, you can see that here is how the raw odometry will behave in terms of uncertainty. So we come from here, then we just apply the odometry over and over, and we know the noise of the odometry. We end up with a very dispersed sample cloud, no? But if you do the scan matching, what will happen is that we are much more concentrated, and our posterior is actually much more compact. We have less uncertainty in the pose and the trajectory of the robot, and therefore we need to have less samples to cover this part of the space. Okay, so the idea is that we want to cover the whole part of the state space where the mass of the distribution is, and the smaller is this part of the space, the less sample we need for covering it. Now, if we just give an idea, what happens if we just do scan matching alone. So we don't do any other post-processing, we just do an incremental scan matching over time by just aligning locally the scans while the robot moves. And we just use this as improved odometry, and we just take those and then use this trajectory as the best, or let's say as our known poses, and we compute an occupancy grid on this. That's what we obtain. So it already looks way better than by just using the odometry. We still have some inconsistency here and there. Up here, for instance, this should have been the same part of the environment. Down here is the same. But we see that locally, these are actually quite nice. And if we use this then as improved odometry for our proposal distribution for our sampling, we get way better results. So the idea then is that we can pre-correct small odometry sequence over time, and then we have, let's say, fake this small sequence as an improved odometry measurement, and then we use this improved measurement as our virtual motion model, okay? So instead of just saying I only consider what the wheel encoder tells me, I consider the measurements for a short sequence, and then I just assume that this is my motion, and then I use this as my motion, okay? And we need fewer particles for doing this because the input error becomes smaller, the uncertainty in the motion is smaller, so I need less particle for covering the state space. If you want to see this on a graphical model point of view, before we had the U which were coming directly from the odometry, and now we have a set of discrete steps, which is k, 2k, and k in this case, where k is the short interval where we accumulate the data and we do the incremental scan matching. And up here we can see that these U now are actually a function of a set of odometry and a set of measurements, okay? And what we use is the measurements from 1 to k minus 1, because we still need the measurement at time k down here for the update of the particle filter. So we use k small odometry motion. Up to k minus 1, we improve the estimate locally with the scan matcher, and then the next step we just use a small increment of the last odometry, and this basically reduces the drift from time step 1 to time step k minus 1. Okay, so that's the idea. And by doing this, we can reduce the number of particles. We can have enough number of particles that we can maintain all the maps into memory, and we can get better results for the fastslam algorithm. Here is an idea, a video. Oh, okay. Cannot show it to you. But the idea here is that the robot starts from here, does the whole loop, at some point reaches a point here which is we call it loop closure, so it comes back to the same place. And as you can see, we still have some uncertainty accumulating over the trajectory path by desampling and so on, but it's quite contained and it's quite small. When the robot arrives here, we can see that the effect is the likelihood of all these different samples with respect to the map at this time will be way different. And it was not different during this path because they were very close together. So the difference in likelihood with respect to the map and what they are, where the particles are actually quite similar. And when they reach this place, then there will just be a collapse in uncertainty there. And we will have then as a final result, let me see if this, something that looks like this. Okay, so it's a very good map, and the robot had actually a path around here and went around this place. We are able to reach this level of accuracy and quality because we now can handle enough particle to represent the full distribution rate trajectory in this environment. Of course, the bigger the environment gets, the more particle we need to have. So there will still be a kind of a maximum size that we can handle with respect to the memory computation. So for the memory consumption that we need to store all different maps. There are some tricks on saving memory in a way similar that we have seen for fastslam in the last lecture, where we had this tree where different particles, different samples were storing part of the landmarks in this tree-based representation. We can do the same with maps. We can just divide the map in small patches, and then we can use the same technique as this tree, where instead of storing a single landmark, we store a patch, and we just share patches around the different particles, so we get down on memory requirements for this. And there are also some other techniques for saving memories which look similar. So the whole point there is that the history of samples comes similar over time, because during resampling steps, a lot of particles, a lot of samples gets duplicated, so they share the same history. And if this part of the history is not modified during in the next steps of the algorithm, then we don't need to actually replicate the exact memory, but we can just store pointers to this part of the history. Okay, so that's the idea there. So far what we've seen is that you can actually employ this fastslam algorithm for grid maps, and we need to use some better techniques for instead of the odometry for our proposal distribution. And here we've just seen that we can use a scan matching procedure to create a virtual odometry which is better and which has less noise and less drift than the real odometry from the robot. Okay, so in principle you can imagine that scan matching is just generating some virtual commands or some virtual odometry measurements which are better than the real one. You can also see this as a potential ad hoc solution. It seems kind of a hack that one does to improve the situations. And the question is that, can we actually do it in a more principled way? This was one of the first solutions to this problem, and therefore there was a bit of trial and error, and that's why they came up with this kind of hacky ad hoc solution. But in principle, you can actually do it on a more principled and general way if you understand what's the reason, what is the reason that the particles number of samples is actually big, and what makes this number of samples or the amount of needed samples decreasing. When we were discussing the particle filter, we said that the closer the proposal distribution is to the target distribution, the less number of samples you normally need. Okay? And the reason is that if you have a very different distributions, then you end up in sampling in part of the state space which is not of high density for your target, and vice versa. So then to get samples to the high density part of your target distribution, you need to sample a lot, because you need to collect samples on the tails of your proposal distribution. So ideally we would like to sample the new pose of the trajectory from this distribution here. Now we like to sample from The distribution that is conditioned on the previous samples that we have. So remember, we still sample in a way that we don't throw away the samples before, but we just build this trajectory step by step by adding small samples to the previous one. And we want to use all the controls that we have so far and all the measurements that we have so far. Okay? So this is basically the target distribution for the single step, the single sample that should be attached to a trajectory, given that this is the trajectory we want to attach it to. Okay? So if you're able to do this, to sample directly from there, then we will have better sampling, maps which are more accurate, and also the need of using less particles. The problem is that we cannot really sample directly from that, because otherwise we don't need to do any estimation. It means that we already have our posterior distribution over the trajectory and the maps, and we're happy with that, and we don't need to do anything else. But what we can do is we can sample from this distribution here, okay? So we can sample from the distribution that takes the previous trajectory, the map that we computed so far, and also and also considers the last measurement from the laser and the last measurement from the odometry. Okay, so we can see this one as this product. So this is similar to what we have done when we were discussing the base filter for this problem here. We can just swap the Z from here to there, and we end up with the likelihood up here. And then we can have on the right side, by just applying base, basically the distribution of the pose given the previous force and the measurement. We know that this one does not depend on the map, given the Markov assumption, so we can remove the map. This one does not depend on the control, again, given the Markov assumption. And then we have a normalization factor down there. So this is just applying the base rule on that, and we know that this is something that we know how to compute, because it's our sensor model. This is something we know how to compute because it's our motion model, and this is just a normalization factor. Okay? So in principle, this looks like a one-step filter that we need to do, one-step estimation process. If you look at laser scanners, what we have is that we have a very peaked likelihood because the sensor is very precise, and normally we have a not so peaked odometry because it's way less precise than the laser measurement. Okay, so basically this tells us that we have two parts: one which is really what we should care about, and one part which is the one that that gives us less information. This gives you an idea why it's important to consider the observation that comes from a laser when you use the proposal, because sampling from here will have a lot of samples on this area that actually will be thrown away, and few samples on this area which will actually be the one which are good. No? This is just the case, but often happen in practice. That's why it's good to combine them together. Now, if you analyze what happens when we combine this, what we'll have is that we'll just, by simplicity, call this product here tau. We have the normalization is actually can be expressed by the integral over the upper part in the x. So it's just a way of making sure this product is actually a distribution and it's not just a product of two functions. And we can then say, okay, this distribution here now is tau normalized. So the only thing that we need to do is to find a way of how we can compute this tau, or if we want to use this as a proposal distribution, we need to know how to sample from this distribution here. What we can think of is how can we actually approximate this part here in a way that is usable for sampling. So if you analyze what happens in here, we have that this part is actually somehow limiting globally where the robot can be, no? Because our odometry, it's something that says, I was here before, I move here around, and the robot might just be in this part of the area. While the sensor model limits us locally. So it says, I'm now looking, for instance, at the door, And whenever I see a door in my environment, I can just be close by to the door, but I can also be in front of many other doors, no? So if you see it graphically, you will have that here, it's our odometry that somehow blocks us globally, because that's the only place according to the odometry where I can be. But then if you consider just the likelihood, and we try to see which is the most likely place I have given this observation, if the environment is kind of repetitive, we can have some peak distribution here, but also some other peaks somewhere else that looks like the place where the robot is at this moment, okay? But since we can limit ourselves with this, what we can do is that we can just try to be around this part here. We do a scan matching around here, and we try to find a way of approximate the product of these two in a way which is easy to sample from. So getting back to the proposal distribution and giving a bit more practical thing, the problem is we need to sample from here, and either we can use any sampling technique we studied so far, so we can, for instance, use important sampling out of these two and so on, or we can try to approximate this product with something that we know how to handle, okay? What has been done in the literature is to approximate this product with a Gaussian distribution. So we just take this full distribution here and we approximate it with a Gaussian. So we need to compute, in a way, a sort of mean and covariance, and then we can sample from a normal distributions as we normally sample from that. So how do we do it? This is visually what this function might look like, this tau, so before normalization. And this is for, let's say, the maximum that our scan matcher reports when it's initialized with odometry. So it just goes around, tries to find the maximum likelihood alignment of its data with the map. And let's say that's here. Then we do some sampling around this. We uniformly sample around this maximum in x, y, theta, and all the directions. And then we compute through, again, the important sampling principle, some weights for them. So we'll have samples which are more, which are higher weight than others. And once we have all these samples, we can then do a Gaussian approximation of the samples, and we have our Gaussian distribution there. So we do not want to do two-stage sampling in there, because we don't want to evaluate too much likelihood function, which are expensive. So the idea is, if we can cover around the maximum of the scan matcher uniformly, and then we can get the Gaussian distribution, then given this Gaussian distribution, we can sample as much samples as we want with very low computational effort, instead of doing the whole important sampling again and again by doing this, okay? So the idea here is to reduce the number of likelihood evaluation. We first do a Gaussian approximation, and then we sample for that, okay? Is there any questions so far on that? All right. Before we go on how to compute this Gaussian approximation, do you remember how to compute? So for computing this, we actually need to compute the mean and the covariance. And the only thing that we have is a set of samples. Do you remember how we compute mean and covariance given the samples in general? So if we have just a set of samples, we do what is called the sample mean and sample covariance. So let's say I have a set of xi. I goes from 1 to n, let's say. I have n samples. I can compute my sample mean by just saying this is equal of 1 over n, the sum of xi, right? Yeah. Do you remember how we compute the sample covariance? Okay, so we subtract each sample with the mean, okay. Okay, we squared, and then? So we sum it up, probably, yeah? And we divide by the number of samples, you say. Okay, so that's the way we do it if this is a one-dimensional Gaussian. If you want to have a multivariate one, this square actually becomes xi minus mu transpose. So we have one rank matrix update in here. Okay? Are you sure about this? Okay, so this is what it's called a bias estimator for the variance, because we are using the same samples for computing the mean as well. If the mean was given, that was the right one. Since the mean is not given and we use the same sample, we lose what's called, so we lose 1 degree of freedom in the estimation. So basically this one becomes 1 over n minus 1. Okay, so that's what it's the unbiased covariance estimator. Now, this means that all the samples have the same importance and all the samples have the same weight in some sense. Okay. Now the question is, we have to go from this case to the case where we have a set of pair, where we have our nice sample, but we also have our weight. Okay. Now, how can we go from here to there? Let's imagine for now that these weights, that the sum of all the weights is equal to 1 for simplicity. No? Do you know how we go from this description to there? So we can also write this thing as something like the sum of 1 over n of xi, for instance. No? And these things can easily be seen as a weight for a sample, no? And also we know that in this case the sum of the weight is equal to 1, because we have 1 over n, sum n times, that's n time divided by n, and it's 1, no? So we can simply go from here to there and say, we can do the same. We have our nice mean, that's equal to the sum of the weights of the xi. No? That's how we have the mean estimate. We can do the same for the covariance. No? That's an equal missing. With the same reasoning. Let's start first with 1 over n, which is the easier way of doing it. So the biased estimator is actually the same form. So we have our nice covariance, sigma is equal to the sum of the weighted xi minus estimated mean, xi minus estimated mean transpose. Okay? Now the problem here is that we cannot apply this one any longer. Okay? Because the -1 doesn't really play well with the weights. Okay? Because we have the same weights up and down for the mean and the covariance in that case. But if we put 1 divided n minus 1 as weight for the covariance, these are different weights than the one we have before. No? And they also do not sum up to 1 any longer. So the way this works is that we need to find the correction factor to have the unbiased estimator. And this correction factor is equal to the sum of all the weights on top. So this basically becomes the sum of all the weights on top divided by the square of the sum of the weights minus the sum of the weights squared. Okay? So the interesting thing is that if now we put 1 over n for all the weights, so if you go to the equal weighted version of this, we will see that once we put this equal when 1i is equal 1 over n, up here we will have 1 because it's 1 over n for 1. Down here we will have also 1 because it's 1 squared. So we have 1 minus, in this case we will have 1 over n squared. You sum for n, so it's n times over n squared. Okay, we simplify them, and if you put things together, this is equal to, down here we have n minus 1, up here we have n. Okay? So since we have the weights inside still in here, this basically gets multiplied by 1 divided by n, because you take the weight, you can put it outside, it's always the same. You can simplify this and this, and you end up with just the sum of the two, which is this part, divided by the resulting factor, which is 1 over n minus 1, and we end up exactly the same. Okay? So that's how you do the unbiased estimator for the covariance there. Now, the way it's been done in the literature, for simplicity, they used the biased estimator for the covariance. But anyway, since we are approximating the distribution with the Gaussian, so there is already an approximation into play, it doesn't make much of a difference, and it's way easier to implement because you don't have to compute the correction factor. But in principle, you can compute the correction factor if you want. So we have the mean computed as a weighted sum of all these uniform samples. Since these samples are uniform, from the importance sampling, we can just say target divided proposal. The proposal is the uniform, so it doesn't count. The weight is the target distribution divided the constant, and which basically means it's the target distribution that we then normalize, no? Because the weight must be proportional to this ratio. The same thing is for the covariance, the same tau, and the normalization factor that we have here is just the sum over all taus. Okay? So that's the normalization factor we consider here 1 over eta. Okay? So it's basically the way to make sure that the sum of the weights is equal to 1. Okay? And exactly, these xj are uniformly sampled around this maxima of the scan matcher. So we have seen now how the proposal distribution looks like, or at least how we can approximate this proposal distribution. Now let's see how we need to change the computation of the weights, no? Because we know that every time we touch the proposal, the weights are computed accordingly to the ratio between the target, what we want to achieve, and the proposal, what we use for sampling. So if we expand everything and just take it the proportional to, so we remove part of the normalizers, so basically we remove the distributions or the functions that do not depend on x, because those are constant with respect to the weight calculation. The weight, again, is a function of x. We can see that our target is our likelihood at this time step, the motion model that moves the previous sample to the next one, times the posterior at the previous time step. Okay? So that's how our target distribution is. If you look at our proposal, we have the distribution here, which is the proposal we want to approximate, which is x times t, the map, t minus 1, z, and ut. That's what we've seen at the slides before, times the sampling that we already have done with respect to the previous time step, no? Because we have a part of trajectory that has already been sampled, and we have it from before, and we are now sampling the last step, okay? So these things here is actually the weight computation of the previous step, no? Because it's the posterior at the previous time step divided the proposal at the previous time step, right? So weight, target divided proposal, target divided proposal, no? So far we can say that this becomes just the weight that we had at the previous time step. And in case we had a resampling step, if you remember from the last lecture on the particle filter, if you do a resampling, this means you are sampling directly from your posterior. This means that this weight is actually 1 or 1 over the number of particles. Okay? Because we are directly sampling from the posterior, so posterior as a target, posterior as proposal, it's the same thing divided by the same thing is 1, and so the weight is proportional to 1. But that's only the case if we did the resampling step. If we didn't, the particles or the samples at the previous time step, they still keep the weight that they had before. No? So when we do an estimation on the full trajectory, we keep the weight until we do a resampling step. And the same thing is if we do not normalize for the normal Monte Carlo localization. So basically, if a sample is propagated over time, you need to keep the weight and you need to multiply the weights over and over time. Whenever you do a resampling, you basically reset the weight to 1 because you're sampling directly from the target distribution. So that's the idea on how these things works. In practice, what happens if you forget to do to bring the weights with you over time? Basically, you are forgetting part of the distribution that is the difference between target and proposal. Okay, so if I just forget to carry the weight over one step, basically I'm not carrying the history. I'm not carrying the full history, but I'm only carrying the history of the proposal distribution, but not the history of the posterior. No, because we need to care of this mismatch. Whenever we do a resampling, we just do all the histories then again in the sample set, and then we're happy with that. Okay, that's about the weight here. Now let's try to analyze the upper part again. We know this is what we've seen before, up here, it's the same. Now we just expand our proposal as we've seen the slide before, and we know that this is equal to the likelihood up here, the motion of the single particle, and the normalization factor which is there. No? So if you look at the normalization factor, this is just the integral of this product up here. And if you now look at the similar things that can cancel out, these two actually are the same, so they can cancel out. These two are actually the same, they can cancel out. And this goes on the upper part. So we end up with basically the product of the weights of the previous time step and this normalization factor up here. Okay? So now, again, we are with an integral of the product of two distributions that we do not really know how to compute in closed form. But what we can do is we can try to do what's called the Monte Carlo integral approximation. No? So the idea here is that, let's suppose this is tau, so the generic function that we want to compute the integral. If we do not know how to compute this integral, we can just sample from uniformly. That's how we do the Monte Carlo integration. We sample uniformly in the domain of x, and we evaluate this tau at the sample point, and then we take the integral becomes a sum, and we normalize it with respect to the points. So what ends up is that we sum up the tau at several uniformly sample points, and then we divide this whole sum by the number of points that we used. Okay? So this is the way of computing an integral. It's called the Monte Carlo integration approach. Now, one can do several ways of doing the sampling. So this particle filter and the Monte Carlo integral computation are actually very strongly and tightly connected. But the thing that you should consider right now here is that we actually already have these samples because we sampled before from the SCAM method, okay? And we can just use the already computed normalization factor for the weights that we used for computing the mean and the covariance before, and just use the same value, okay? The reason is that this distribution, as we have seen before, looks something like a very peak distribution here, and a very unpeak and smooth distribution there. The part before and after are actually almost zero. So the value of the function of this product, even if here there is another very highly peaked distribution over and over and over, they will be multiplied by something very close to zero, so they will all be brought down, which basically means samples here I have very low value for tau, so also very low contribution to the integral. The only samples that actually will have an interesting contribution to these integrals are basically the samples around this area, okay? Or maybe the samples more on this area here, because this one also goes to zero quite rapidly since it's very peaked. And these are exactly the samples that we the interval that we used for computing the samples around the maximum of the scum match. Because we took the maximum here, we went down, we took somehow an interval around here, which is again the area with where the mass or the density of this function is much higher. Okay? So we can again approximate this integral by just the sum, simply as it is. And we only need to compute it once. So magically or by chance or luck or however you want to call it, we don't need to compute it twice because this normalization has already been computed before. Okay? Any questions so far on this? This, the step, the approximation, and so on. No? Okay. So how does this proposal look like according to the environment, according to the measurement? So here we have three sketches. So if you are in open space, so if there is no measurement that can actually collapse us, what we'll have is that this likelihood will be almost flat because there is no observation that I can use beforehand, and we'll basically just end up on something which is close to the odometry, and that's it. No? So all the samples will be basically around odometry. The scum matcher will have almost no impact in that. If we have a long corridor where we basically are constrained on the left and on the right side, but there is no constraint on the top side, our likelihood will be much smaller here, so very, very tight here. But in this direction will be very long because there is nothing that can constrain the laser in this direction. There is no wall here, no wall here, so it's freely to go wherever it wants. If we have a constraint on all these three directions, then we will have a very tight proposal that is constrained left and right by these two walls, but also on the top by this other wall. So basically here the idea is that we exploit the structure around the robot to have an improvement on where to put the samples correctly. Okay? This also means that we will never sample something that has a mismatch with this wall, because the only way to get like double walls or some problems is to have samples which are in this direction. No? And by having a proposal which is very tight in this direction, we very unlikely get those samples. Okay? While if we were using this proposal, the odometry, then we would very likely to get samples all around here. And this will be waste of computation or waste of memory if we need to keep all these maps into memory. Okay? Any questions so far? No. Okay, so another thing that actually we should take into account is also the effect of resampling. So the effect of resampling is somehow that limits the memory of the filter. What does it mean, limits the memory? It means that we forget this history of samples in some way, but actually the main effect is that we remove diversity in our particle set. Okay, so can I delete this? Okay, so the problem here is that imagine that we do resampling every time. We will end up with, imagine that we have a lot of different trajectories. They all go like here and like there and so on. So we have a lot of diversity on the distribution of the trajectory. But whenever we do resampling, what we will do is that some of this trajectory will be kept multiple times, and some of them will be eliminated. So we will get with something that maybe remove this trajectory here, and then maybe removes also this other one here, and you will end up with few less trajectory. And if you do it over and over and over, then this one will then maybe go on different, each of them over time will go different trajectory, but the history behind will still be the same. You do again another resampling, and you will maybe eliminate completely this history, and you will just be left with these few trajectories around. And at the end, if some of them, they come back here, no? And none of them will actually end up in the right place, because maybe there was small mistakes on this part that we didn't really consider. The loss of diversity here make that we cannot recover, okay? And therefore, we try to reduce the amount of resampling step to keep this diversity into play. Here is the graphical picture of the same thing I've showed there, and it's here. We start with this particle that gets duplicated and so on, but at some point, the only sample that survives in the past is this one, okay? For localization, it's okay to do the sampling every time because we do not care about the history. We just care about the last pose. But for the mapping is not the same as any longer because we care about the whole history of the trajectory. Okay? So that's the idea here. So to reduce the amount of sampling steps, there is another technique which is called a selective resampling. And the idea is that we need to resample for achieving convergence, but we only resample when it's actually needed. Okay? And the idea is that how can we say, okay, now we need to resample because we are sure that we are not, on one side, that we are converging, and the other side is that we are not losing diversity any longer, okay? And the idea here is that this, there is a function which is called the number of effective particles, and it's basically proportional to the variance of the particle cloud. And this value here somehow reflects the amount of samples that have a full weight, okay? So that the amount of sample whose weight is very high with respect to the one which is very low, okay? So if all the weights are roughly the same, this number here will be very close to 1, okay? But if some of them are very high and some of them are very low, this number will be very close to 0. It's going to 0, okay? The reason here is that imagine you have a lot of particles or samples with a low weight, okay? Since these are normalized, this is very close to 0 because the sum of them must be 1. They all have roughly the same, so this will be around 1 divided by the number of samples that we have. We take the square of it, okay, and then it gets even smaller, and then we do the sum of this, and we will have, again, as we've seen, okay, now it's disappearing, as we've seen in this way, this will be n divided by n squared, and then we simplify, and basically it's equal to n. So it tells us if the weights are the same, this is actually equal to n. If we have few samples with the high weights and the other one with very low weights, we will have that some of these weights are very close to 1, okay, and some other are very close to 0. So this sum then will just be dominated by the one that are very close to 1. And if you then do the computation here, you will get something that goes slowly close to 0, okay? So basically this number here tells you an idea on how many particles are actually effectively into play that represent the mass. And you can use this to thresholding a resampling step. So basically you can say, I want to keep roughly this percentage of samples alive, and whenever this percent of samples that you can get out of this goes below this threshold, you act a resampling step so that you repopulate the distribution with the new samples, okay? So the idea is most of the times we use n divided by 2, so we just say, I want to keep at least 50% of my samples alive in this process, and we just do a resampling step whenever this number of effective particles is less than n divided by 2, okay? So that's just a way of an heuristic for computing it. Please be aware that for making this, for having this value to be meaningful, this weight needs to be normalized. If they're not normalized, you can have an arbitrary number here that doesn't tell you anything about the distribution, about the variance of this distribution, okay? Any question on that? Okay. So here you can have an idea on how this number of effective particle behaves in reality. So we start here with our filter, and we see that, so I think the robot starts around here. It goes up here, and you can see that there is a slow decrease of this number of effective particles. And that's because over time, some of them have a higher weight, some of them have a lower weights according to how they are sampled. Then the robot goes around here. It does a second, it does a loop here, and then you have a kind of decrease in the number of samples up there. And then it goes a resampling step, so you go from a number of effective sample of around 15 up again to around 30, and that's just because of the re-normalization of the weights. Now all the particles have the same weight, is 1 over n, the number of particles. And then you go again around, and then the robot is in a place which is which he already has seen a bit. So when he does scan matching around, I think I bet it's on this loop. When he does scan matching around this loop for a while, is always very well aligned, because this is a part of the environment he already has, and it's always aligning with the environment. So the difference in the weights is very small. That's why they kind of keep to be almost the same. And then at some point it goes around again and reaches here, and you see there is a huge drop again because resampling takes into play. Okay, and again. So this is the typical behavior of this amount of particles. When you explore new part of the environment, you tend to decrease a bit, but not too much. And then whenever you start re-entering a part of the environment that you have seen already, it starts to slowly decrease. And then you do a resampling step, and then it goes back up. Okay, so that's how it behaves normally. Yeah, that's basically what I've said already. So here is the map again of the Intel lab. We have seen it before with the hacked ad hoc version of fastslam. Now we can see what happens if you do the more formal way. The idea here is that we have a 5 centimeter resolution during the mapping process, 1 centimeter resolution for the final one, so we can re-render then all the data with the higher resolution. And we needed to use around 15 samples for obtaining this. While in the previous case, we had to use around 30, 50 to obtain something on similar level. Okay? So you can see that with only 15 samples, we are already able to get something reasonable out of it. Okay? And the reason is that the scan matching is actually quite good, because the laser is quite precise. So as you have seen before, if you just do the scan matching, you are already almost close to the right solution. So we just need to keep a bit of variation so that whenever we do the full loop, we come back, we have enough variance here in the samples of the trajectory, so that we can have a good coverage of where the robot could be after the big loop. Okay? In principle, the number of particles that we have, so in this case 15 was enough, it's very hard to know how many you need in advance. And they all depend basically on how much uncertainty you need to cover in the worst case. And this depends on the size of the environment. It also depends on the way the environment is traversed. Okay? So, because uncertainty accumulates over time, accumulates over when the robot goes into unexplored area. So the longer is this path, the more uncertainty it accumulates over time. So if you do a lot of close exploration, so if you always kind of explore a bit and comes back, explore a bit and comes back, and so on, in this kind of looping actions, then you can keep the drift contained, and then you need not so many particles. If you instead go on very large exploration phases, you accumulate a lot of noise, and then you come back, then you might need a lot of samples to get something meaningful. So it's not clear how to compute them, and they all depend on the worst case path. So in principle, as a take-home message, if you use approaches like this, so fastslam-based or particle filter-based approach for mapping, knowing how to drive the robot for collecting the data is very important. We'll see Not in this lecture, but in the in Intro to Mobile Robotics, there was a part of the lecture on exploration or exploration-driven mapping and so on, where basically the robot is autonomous in exploring the environment, and to know where to go, it also takes into account these aspects of how much uncertainty I will accumulate, and is always trying to not accumulate too much uncertainty during an exploration stage. Okay. Any question on that? All right. So here there should be a video. I hope this works. Looks like. Here is again the video in action, how it works. So you can see that there was some diversity in the particles, and it came here and it goes down. Again here, you can see that some of the black trajectory are disappearing, and that's because of the resampling actions that take into place. You see that there is not much diversity on the core bigger loop, but that's not a big problem, because there's actually the only way of keeping this rigidity in there is to really have a very small uncertainty environment over the whole loop. And then you can say that the robot is exploring, is accumulating a bit of uncertainty, and then it comes back here and is at some point exactly reducing that uncertainty again, and it will go over and over with this. Now it's doing the same loop, but on the other way around. And as you can see, I think at some point we'll remove this whole uncertainty here. It will see here, and we'll start to do a resampling step. No, okay, it doesn't do it. So it was then going away here, and then was doing a resampling and removing some of the black particles there. And this is a distribution over the trajectory, so all these black thick lines are different samples, and the red one that you've seen here was the one, in this case, with the highest weight. No? So in some way it resembles the most likely map, although it depends on how you, again, define what is the estimation that you want to have, and the same things we said on the grid maps in the lecture before. There are several ways of defining a point estimate. And in this kind of approaches, what is often used is to take the sample with the highest weight. Here you get the map that has been computed here around the campus. So I bet we are here somewhere on the last floor. That's building 52, 51, the 74, 79, the Mensa, and so on. And we drove the robot all around the campus and used this algorithm to compute a map of the Freiburg campus on the fly. We used 30 particles for that, and we had 1.75 kilometers of the full trajectory around there. There is also another data set which is called the Infinite Corridor at MIT. So there is a corridor which is very, very long and is connecting several different buildings at the MIT in Boston. This is the very long corridor that you can see there. And again, we were able to, so there were some colleagues at MIT collecting the data here, and then we used this algorithm to compute the map from the data. This is how you can see it from an aerial view. And another approach that actually uses a very similar technique is vacuum cleaners. This is from, I think it's from Samsung, but I'm not 100% sure. That also has a way of computing the map as a kind of cheap sensor that measures the distance around, similar to a laser scanner, and it computes the map of the environment, and you knowing how the environment looks like, he knows which is the best strategy to explore the environment and so on. Okay? Any question on that? Okay. So far we said that we can approximate this proposal with a Gaussian center at the maximum of the scan matching. Okay? The problem now is that we are basically approximating a distribution which can be multimodal with the distribution which is unimodal. No? So the problem here is that sometimes we have two hypotheses, okay, and we just basically remove one, and we just say we want to focus on only one of them, okay. In many cases, what will happen is actually that these two hypotheses that we have from the scan matcher are not that close, are actually quite far away, and they do not intersect the odometry. So we often have, let's say, an odometry like this, and if you look at the likelihood, we'll probably have something here, and then maybe we have something here and something here, okay? But sometimes what happens is that we actually have multiple of these that can intersect the odometry. And if that's the case, then we might fail just because we are neglecting part of our distribution. So to say in a different words, the Gaussian approximation that we do is too crude, is too rough, and it's not a valid assumption or a valid approximation any longer, okay? And this is what you can see. For instance, you have a very long trajectory, and then you might end up in different rooms, for instance, of the same environment or so. So you will have a lot of different modes where you could be. Now, the problem is that the Gaussian assumptions fail in these cases, and we try to analyze how often this assumption holds and how often this assumption actually fails. For doing this, we can do some statistical tests. Very famous one is called Anderson-Darling test. It's a statistical test on the likelihood ratio to check if a certain empirical data actually can come from a known distribution. And you can do it for the Gaussian case, and there are some tables that tells you if the test is within certain values, then the distribution is very likely to be a Gaussian. If it's not in these values, it's not likely to be a Gaussian, and so on. So it's a common statistical test to see if those data actually arises from a typical distribution. We can do it with on the approximation, and also considering the real data that we get there. And what we can do is we can use this KLD, is a divergence. A divergence is a kind of distance measures between distributions. It's not a real distance, that's why it's called a divergence. It's because it's not symmetric. So sometimes you have different divergences if you change the two distributions. So if you say x minus y might be different than y minus x. Okay, so that's the reason. But this is a standard way of measuring differences between distributions. So if you do this test, we actually end up that on the data set that we have seen, we have that for some of them, like the Intel, we have that the Gaussian approximation is quite good, so it passes the test around 90% of the time, in some other 84, or in some other 75. So basically, in general, the Gaussian distribution is a very reasonable approximation in roughly 75% of the cases or 80% of the cases. In some other cases, you can see that it's non-Gaussian, but it's still unimodal, which basically means in these cases, we can still live with the Gaussian approximation, and to be sure, we can just inflate a bit the variance so that we cover also the rest. No? That's basically if you have distributions that instead of looking like a real Gaussian, which are, let's say, this, they might look something like this. No? That's something which is non-Gaussian. It's definitely multimodal, but this one you can actually approximate nicely, for instance, with the Gaussian, or you can have distributions that are actually skewed, so they are like this, but still they have one mode, so you can still approximate it with the Gaussian maybe like this. No? So you can still cover a good part of the state space with the Gaussian. The problem sometimes is that we have multimodal, which are very hard and cannot easily be approximated with a Gaussian in this way. No? And this happens around 6 to 7% of the case. So in these cases, we're actually making a mistake, and we should consider different proposal distribution for that. So in the literature, what has been analyzed is that if you have this case, you might end up in maps that looks like this. Okay? And that's because here you had bad samples, and since you only sample from the bad part of the state space, you do not have the right samples in your distribution. So basically, you cut out part of the support of the distribution, which was the support where the true values of your variable was in there. No? So you will never be able to recover for that. But this is the case where these things are actually quite bad, where you have two modes and you have a clear separation between these two modes. So what we did before was we took a Gaussian approximation by saying I take the scam matcher here, I then move it around uniformly, and I compute my mean and covariance. You can do something different if you just change the order of this operation, because you can just say, instead of doing this, the odometry, scam matcher, and sample, you can just take, this is the uncertainty of my odometry, I can just take different samples, and then I try to do a scam matching aligned with these different samples. Okay? So before we were just taking the mean of the odometry, doing scam matching, computing the this normal distribution approximation, and then sampling from this normal distribution. In this other way, we sample directly from the odometry, and then we do a scam matching to align this sample with respect to the data that is in there. If you do this, we end up in a way better map for this case, because we're actually able to consider these different modes when we do the sampling from the proposal distribution. Okay? If we now do a bit of proposal error evaluation, so let's say which is the divergence of the proposal distribution that we have as approximation and a true distribution evaluated by just in a discrete way. So we just have a discrete grid and we just really have a full evaluation of this distribution. We end up that in some cases we have a high error, so a divergence more than 0.4 if we just use a Gaussian proposal. But if you do this two-step sampling, which is a bit more expensive computationally, but not too much, we end up that all this part here are actually eliminated, okay? Because all these errors were coming from these multimodal distributions that we should consider, and if we do not do that, then we will have this approximation error up here. Okay, so that's as a take-home message from the effect that this two-step sampling has is, of course, it's better for modeling multimodal distribution, and in some way you can say that is the real advantage is exactly in this case. So if you just have unimodal distribution, you do not really have many differences and almost no differences. So in this case where it's slowly multimodal but simply so very similar to a unimodal, you will have some differences. In this case where it's just skewed, you might have small differences but not too much. The reason is that the second step will anyway do a scam matching, so if you end up in the same minimum of your maximum likelihood, you will end up anyway in the same samples that are computed at the end. There is a minimal overhead because you need to do multiple scam matching instead of a single scam matching and then an approximation of the likelihood of the distribution, so computing this mean, computing this covariance. But sometimes this small overhead is actually worth the price to pay. So do we actually really need this or not? As a take-home message, on one side, if you have this Gaussian approximation, sampling is more efficient, so you can generate a lot of samples almost at the same cost, because the only cost you have is the cost for the approximation. But in the other case, you need to have, the more samples you have, the more costly it becomes. Not because you don't have an easy sampling procedure, but you need to compute this scam matching for every particle that you need to use. On the other hand, if you only use the Gaussian distribution, you might have problems in your estimation. so you might end up with maps which are not usable. And if you so looking at the data set that actually we have seen so far, you see that 3 to 6% of the cases this multimodality actually happen, and this can really make things problematic for the mapping. So the idea is, if you can afford the overhead, then do it. If you are in very limited resources settings and you feel like having more samples is better than having this overhead on the sampling, then use the Gaussian approximation. If you know that your environment is also not too ambiguous, so if there are places which are quite unique, then maybe this 3 to 6% goes more towards the 3% level or even less. So you might not end up in this problem, so you can still use just the Gaussian approximation and so on. So that's, as usual, there is no clear answer. There are pros and cons, and you need to evaluate it on the application and the task at hand. So to conclude the lectures of today, we see that this fastslam's idea, so this Roblek realization, this factorization of the distribution with sampling just the trajectory and having a way of computing the statistics of the map in analytic form, can also be applied to grid-based maps and not only to feature maps. But the twist here is that we really need to consider proposal distributions which are closer to the target, and by just using the odometry as proposal distribution, we do not obtain good results because the amount of samples that are needed are very high, and by the need of storing a map for each sample, we end up that we cannot use enough samples for the problem at hand. So we need to focus on a better way of obtaining the samples, which basically means we need to focus on how to improve the proposal distribution. We have seen that you can do this by basically having a virtual odometry by just applying scan matching in chunks, or you can do it by computing what's called the optimal proposal distribution. So it's the distribution that takes into account the last measurement in the distribution in the proposal phase. And we have seen that we can do it in two ways. One is that we take a Gaussian approximation of that centered at the scan matching optimum, where we take this optimum from the scan matching, we uniformly sample around that, and from this sample we compute a sample mean and sample covariance, and we use this means, this covariance, to sample again new samples for the particle filter. So there is these two-step samplings where we say take the odometry, scan matching, take the maximum, uniform samples, compute mean and covariance. This is now our proposal, and then we do the sampling of the proposal. Or we have seen that you can do it differently, where we do, again, another two-step procedure, where we do sampling from the odometry. For each sample, we do a scan matching, and we use exactly these scan matched points as our samples for the particle filter. Okay? So these are the two ways we can do this. We have also seen how to do selective resampling, so that we've seen that if we do resampling at every step, we lose diversity in the history of the trajectory. So we only want to do resampling at a specific point in time, and to know when to do it, we can consider the variance of the sample set that we have, so the variance of the weights, something that we call the number of effective particles. And if this number is below a certain threshold, usually 50% of the samples that we have, we then trigger a resampling step. And this is to be sure that we keep enough history until the distribution of the samples is peaked enough that we can do a resampling step, because we are not losing history anyway. We also seen that all these techniques actually becomes in a substantial reduction of the number of particles that we need for the final estimation problem. Therefore, we are able to store all the maps in a modern computer, and we don't have too much problem with memory requirements. With respect to the literature, this part of these approaches are not really in the book, so that's a small chapter on how to do grid-based fastslam, where it's just written, take fastslam and use mapping with non-poses, so not much of the details which are in here, but there are a few research papers. This one down here from Henel, Burger, and Tal describes how to do this chunk scan matching, so this improved odometry by just saying I do a scan matching for a small chunk, and then I use this as an updated or improved motion model, and I sample from that. This one is the paper that describes this improved proposal and the selective resampling step. And this last one is the one that describes and analyzes the effect of this unimodal proposal distribution on the final estimate. Okay? Then this approach actually is also been released open source by the lab here, the IS lab. And you can find the C++ code in openslam.org, and it's called gmapping, this code package. You probably find it also some wrapper in ROS on a lot of other robotics-related toolboxes. That's it for today, and if you have any question, just ask, or we can finish here. Questions? No? Oh, you? No? Okay, then recap on what happens with the lectures. Monday, there will be again another lecture, and this will be the last one for the year in terms of lectures. The next one will be in January, I believe the 18th or 19th. I don't remember now which day is exactly the Monday there, but the Monday of that week. There will be exercises in the remaining of the days. No exercise the day right before Christmas and right before the 7th. So I have to take the calendar, but I think then more details on when the exercise will be, either Alex or Noah will tell it during the exercise section. Okay? Thanks for coming here, and see you on Monday.